chapter number 8, Quantities and Chemical Reaction. During this chapter and this module, we'll be talking about to recognize the numerical relationship between chemical quantities in a balanced chemical equation. We're also going to learn how to carry out mole to mole conversion between reactants and products based on the numerical relationship between chemical quantities in a balanced chemical equation. Also, we're going to learn how to carry out mass to mass conversions between reactants and products based on the numerical relationship between chemical quantities in a balanced chemical equation and molar masses. Also, you will going to learn how to calculate the limiting reactant, the theoretical yield, and the percent yield for a given amount of reactants in a balanced chemical equation. And finally, you're going to learn how to calculate the amount of thermal energy emitted or absorbed by a chemical reaction. So let's talk first about an example that you may know, and we're going to make some pancakes. So sometimes we need to look for a recipe that the recipe gives us the numerical relationships between the ingredients and the numbers of pancakes. So the recipe for pancakes, making them from scratch, usually is 1 cup of flour, 2 eggs, and half of teaspoon baking powder. And all this three combination will produce 5 pancakes. So relationship between ingredients help us to determine how much of the product will be produced. So if we have 2 eggs, we know that because the recipe tells that 2 eggs will produce 5 pancakes. The recipe shows the numerical relationship between the pancakes ingredients. If we have 2 eggs and enough of everything else, we can make 5 pancakes. So we can rewrite this as a ratio. This relationship, we can rewrite it as a ratio, and we can say that 2 eggs is equal to 5 pancakes. 2 eggs will produce 5 pancakes. So this ratio could eventually be what? A conversion factor, because we have two different units. We have eggs and we have pancakes. If we have one of them, we can determine the other one. Okay, so that's why this ratio will be converted to can be converted to a conversion factor. So what this has to do with a chemical reaction? We have something that is known as stoichiometry, that is the relationship between ingredients in a chemical reaction. The numerical relationship between chemical quantities in a balanced chemical equation is called the reaction stoichiometry. We can predict the amount of products that form in a chemical reaction based on the amounts of reactants. If we know the balance equation, we know how much of one of the product will be produced by knowing the amount of the reactant. Also, we can predict by knowing that relationship in the balance equation, we can predict how much of the reactants are needed to form a given form of product. So if we want to produce 10 pancakes, we can determine how much of each of the ingredients we need to produce that amount of product. Also, we can predict how much of one reactant is required to completely react with another reactant. So we can have all these different kind of relationship. We can obtain how much of the product will be produced if we know the amount of the reactant. We can obtain how much of the reactant we need if we need if we want a specific amount of product, and also we can determine how much of one reactant is required to completely react with another reactant. So let's see here an example. Let's talk about the mole to mole conversion. In a balanced chemical equation, we have a recipe for how reactants combine to form products. Let's see the following reaction. This one is when you combine hydrogen with nitrogen to produce ammonia. Here we have 3 molecules of hydrogen. We have 1 molecule of nitrogen, and this combination will produce 2 molecules of ammonia. So here we have the balanced chemical equation. Is balanced because we have in the reactants 3 times 2, 6 hydrogens, and in the products 2 ammonium each one has 3 hydrogens, so this will have 6 hydrogen. So we have 6 hydrogens in reactants and 6 in product. And in the reactants, we have two nitrogen as well as in the products because this reaction will produce two ammonium. Each of them has one nitrogen, so that's why we have two nitrogens in the product. So that balance equation shows that three hydrogen molecules react with one nitrogen molecules to form two ammonium molecules. So this relationship between the amount of molecules of the reactant product can be expressed as ratios. So we can say that three molecules of nitrogen react with one molecule of nitrogen. Three molecules of hydrogen reacts with one molecule of nitrogen, and this will produce two molecules of ammonium. But most of the time, we don't talk about molecules. Most of the time, we talk about moles. But we can use the same kind of ratio and relationship. We can say that 3 moles of hydrogen that react with 1 mole of nitrogen will produce 2 moles of ammonia. So this is the ratio between each of them. Okay, but remember that to produce one conversion factor, you just need a ratio of two of them. Okay, but this is basically the total expression of all the possible ratio that we can combine. We can combine, and we can say that 3 moles of hydrogen will produce 2 moles of ammonium. That 1 mole of nitrogen will produce 2 moles of ammonium. That 3 moles of hydrogen will react with 1 mole of nitrogen. So we can produce all those kind of relationship between the uh, reactants and products or between also them. So for example, this is the same reaction, 3 moles of hydrogens plus 1 mole of nitrogen producing 2 moles of ammonia. If we have 3 moles of nitrogen and more than enough hydrogen, we have a lot of this is an excess of hydrogen, how many moles of ammonia can we make? Okay, so we want to go from moles of nitrogen to moles of ammonia. And we need to look there for the conversion factor that we can obtain from the coefficients of each of the uh, compounds or molecules that are part of the chemical equation. In this case, the we want to go from moles of nitrogen to moles of ammonia, so that the ratio is 1 to 2. Okay, so it's 2 mole of ammonia and 1 mole of nitrogen. 2 moles of ammonia will be produced by 1 mole of nitrogen. This ratio is obtained from the balanced chemical equation. Okay, when we want to go from moles to moles, remember that we always look for those coefficients, okay, in a balanced chemical equation, and that will obtain the conversion factor to obtain eventually the amount of moles of ammonia that we produce by 3 moles of nitrogen. So now we can calculate and use this conversion factor here. 3 moles of nitrogen, we cancel the units because these are dividing this by this, and then we multiply this times this, so we cancel the units of nitrogen. We have now the units of mole of ammonia, and 3 times 2 is 6. So 3 moles of nitrogen will produce 6 mole of ammonia. Now, sometimes when the octane is burned, octane is basically the fuel that is in the gasoline. Okay, the balance equation for the combustion of octane basically shows that 2 moles of octanes require 25 moles of oxygen. Okay, so when you're burning octane, 2 moles of octane will be burned by 20 by 25 with actually with 25 or needs 25 moles of oxygen, and this will produce 16 moles of carbon dioxide plus 18 moles of water. Okay, so this is basically the reaction that is occurring when you're in the engine of your car is working. Okay, is doing a combustion of octane, so it needs 25 moles for two, or yeah, for two of octane will need 25 moles of oxygen. But sometimes you don't have a lot of oxygen, and because of that, the octane is still doing combustion, but it will produce some pollutants such as carbon monoxide and ozone. So these are basically molecules that affect our environment. Okay, they basically are very hazard to our environment. So that's why in 1990, the amendments to the Clean Air Act required oil companies to put additives in gasoline that increased its oxygen content. So that's why you sometimes put additive to the gasoline, because that will allow you allow the gasoline to allow the engine to have more oxygen so that when the combustion of octane is produced, it will produce carbon dioxide and water, not carbon monoxide and ozone, because these are really, really dangerous. So let's talk now about how to change from mass to mass, doing a mass to mass conversion. We saw the example before when we went from moles to moles. So now let's go to mass to mass. A chemical equation contains conversion factors between moles of reactant and moles of product. Okay, so when we're looking to a chemical equation, we're looking there of to coefficients and the molecules that are part of those coefficients. Okay, so we are looking for the ratio in moles, okay, not in mass. So we are often interested in the relationship between mass of reactant and mass of product because most of the time when you're going to do a chemical reaction, you need to weigh a specific amount, okay, of any reactant. So that way the unit is the weight is a mass. Okay, so that's why you need to convert from mass of reactant to mass of products. So basically the general outline for this type of calculation, if we want to go from mass of A to mass of B, you need to go through this map. First, you need to change the mass A to the moles of A. Then we change moles of A to moles of B, the second compound. It could be a product or also it could be a reactant. So we can start here with that reactant, and A could be a reactant and B could be a product. Or also A could be a reactant and B could be reactant B. Okay? Or A could be a product and B could be a reactant. So this is the same map that we can use, okay, for any relationship that wants to have in a chemical equation. It could be A could be reactants, B could be a product. A could be a product, B could be a reactant. A could be a reactant and B could be a reactant. Okay, so it doesn't matter. So this is the map is going to be the same, and the process is going to be this is going to be like a template. Okay, so how we can convert from mass of A, that the unit mass most of the time is gram, to moles of A. So we want to go from grams to moles. What we should use here? So we need here the molar mass, because the molar mass of A will go from grams of A to moles of A. Now, now that we have the moles of A, we need to turn to moles of B. So what we should use here, what conversion factor we need here to go, or from where we can obtain the conversion factor to turn from moles of A to moles of B? From the ratio from balance equation. Okay, the ratio from the balance equation is the one that is going to show us how many of each we need, okay, to obtain that conversion factor. And finally, to change from the moles of B to the mass of B, we should use the molar mass of B. So let's see an example. We have here the reaction of octane. 2 moles of octane plus 25 moles of oxygen will produce 16 moles of carbon dioxide plus 18 moles of water. So the question is, what mass of carbon dioxide is emitted by an automobile per 500 grams of pure octane used? The balanced chemical equation gives us the relationship between the moles, okay, between octane and carbon dioxide. So that ratio is what? Is 2 moles of octane will produce 16 moles of carbon dioxide. So that's the ratio and eventually the conversion factor that we're going to use. Now, before using that relationship between the moles, we must convert from grams to moles, because our first data that we have here is 500 grams of octanes. So we need to change the grams of octane to the moles of octane. Once we have the moles of octane, we do that by using what? The molar mass of octane. We can change from the mass of octane to the moles of octane by using the molar mass. We're going to see that in a few seconds. And then that we have once we have the moles of octane, we can turn to the moles of carbon dioxide by using the relationship or the conversion factor from here: 2 moles of octane and 16 moles of carbon dioxide. And once we have the moles of carbon dioxide, we can now use the molar mass of carbon dioxide to turn moles of carbon dioxide to the mass of carbon dioxide. That is what they are asking in the question. So this is basically the solution map. We have the mass of carbon of octane. We need to turn the mass of octane to the moles of octane by using the molar mass of octane. And remember that we can invert this or convenient if we need to put the unit of gram of mass in the bottom or mole in the bottom, whatever we can invert as and represent the conversion factor the way that we need it. So then by using the molar mass of octane, we can turn out, we have the moles of octane, and we can convert to the moles of carbon dioxide by looking at the ratio between octane and carbon dioxide. That is 16 moles of carbon dioxide will be produced by 2 moles of octane. And once we have the moles of carbon dioxide, we can turn that to the mass of carbon dioxide by using the molar mass of carbon dioxide. So in other words, here we have the solution. Here is the mass of octane, the molar mass of octane. By doing this mathematical operation, we're going to obtain the moles of octane. Then we need to turn from moles of octane to moles of carbon dioxide by using the conversion factor obtained from the chemical equation 16.2, okay? And now we can cancel the moles of octane, this one and this one. We will have the result as in units of moles of carbon dioxide. And now that we have the moles of carbon dioxide, we can turn this to the mass or grams of carbon dioxide by using the molar mass of carbon dioxide. Okay, when we do this, we multiply on the top and then multiply on the bottom, and then we divide the product of the top two with the one in the denominator, and we will have 1.5 times 10 to the third power of grams of carbon dioxide. This is the amount of carbon dioxide that will be produced if 500 grams of octane um, needs to be in a combustion. Now let's talk about other concepts associated with this type of calculations: the limited reactant, the theoretical yield, and the percent yield. Let's go back to the pancakes. Okay, let's recall that original equation. Remember that 1 cup of flour, okay, when we mix that with 2 eggs and half teaspoon of baking powder, we'll produce 5 pancakes. Okay, but let's say that we have 3 cups of flour, 10 eggs, and 4 teaspoons of baking powder. How many pancakes we can make? So to determine this, we need to calculate how many pancakes would be produced by each amount, okay, individual of each of the reactants. So we start first with the cup of flours. 3 cups of flour, we will look for this ratio that is in the recipe. 1 cup of flour will produce 5 pancakes. And when we use this ratio, we multiply 3 times 5. For 3 cups of flour, we will produce 15 uh, pancakes. Okay, if we have 10 eggs, remember that equation said that 5 pancakes will be produced by 2 eggs. So we multiply 10 times 5 divided by 2, and this will be equal to 25 pancakes. So with 10 eggs, we can produce 25 pancakes. And finally, we have 4 teaspoons of baking powder. The recipes mentioned that with half of teaspoon baking powder, we can produce 5 pancakes. So this is basically the conversion factor, okay? And for 4 teaspoons, we can produce 40 pancakes. So we can see that uh, for each of the ingredients at this amount, we can have 3 different amount of products, okay? But what happened if we mix all this together? Okay, we can the number that uh, 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 the number that we can have enough will be for 15 pancakes. Okay, because we don't have enough flour to produce more than 15. Even though we have 10 eggs that will produce 25, the 3 cups of flour limit this production of pancakes. Okay, so here we have that 15 pancakes will be produced by 3 cups um, of flour. 25 pancakes will be produced by 10 eggs, and 40 pancakes will be produced by 4 teaspoons of baking powder. So this reactant is the limiting reactant because it's limiting the other ones to 15 pancakes, even though you have a lot of eggs to produce more than 15. But because you have this amount of flour, you are limited to produce the most 15 pancakes. Okay, so this is known also as the theoretical yield. This is the amount that you can expect if you don't have any problems doing those pancakes. Okay, so we did it. If this were a chemical reaction, the flour would be the limiting reactant. Okay, and 15 pancakes would be the theoretical yield. So suppose we cook our pancakes, but we accidentally burn three of them and one falls on the floor. So even though we had enough flour for 15 pancakes, we finished with only 11 because three of them were burned and one fell to the floor. Okay? So if this were a chemical reaction, the 11 pancakes would beat our actual yield. Okay? The actual yield is what you experimentally produce. Okay, the one of the theoretical yield, you calculate that with a pencil and a calculator. So this is important. Okay, the theoretical yield, you calculate that to obtain what you're expecting to obtain to produce. The actual yield basically is the experimental part. How many you can create when you combine all the other reactants. This is the amount that were produced by that reaction. So the amount of product actually produced by a chemical reaction is the actual yield. So the third part is the percent yield. And the percent yield is an equation, okay, that is basically the percent of the theoretical yield that was actually attained. You divide the actual yield divided by the theoretical yield. Okay, so the actual yield was 11 pancakes divided by the theoretical yield, that is 15 pancakes times 100%. 100, actually, this will be equal to 73%. This is the percent yield. Okay, so this percent is wrong here. Is the actual yield divided by theoretical yield times 100. That will be the percent yield. So since four of the pancakes were ruined, we got only 73% of our theoretical yield. The actual yield of a chemical reaction must be determined experimentally and depends on the reaction condition. Okay, the actual yield. While the theoretical yield, you're going to obtain that by doing calculations in a paper, in a piece of paper, one pencil, and a calculator. Okay, the actual yield is almost always less than 100%. Non-chemical reaction is 100% of yield. Okay, most of them sometimes because handling, you lost some of the reactant, you lost some of the product, so that's why none of them are 100%. Some of the product also does not form. The product sometimes is lost in the process of recovering it, so that's why never any chemical reaction is 100%. So to summarize, limiting reactant or limiting reagent is a reactant that is completely consumed in a chemical reaction. That's the limiting reactant. The theoretical yield is the amount of product that can be made in a chemical reaction based on the amount of limiting reactant. The actual yield is the amount of product actually produced by a chemical reaction. And the percent yield is actual yield divided by the theoretical yield times 100. So I want to emphasize that the theoretical yield, okay, you need to calculate this by the amount of the limiting reactant. So you need to first obtain which one is the limiting reactant, and by using that, you then calculate the amount of product that will be produced. So the theoretical yield will be calculated by using the amount of the limiting reactant. So let's see the following example. Here we have 1.8 mole of titanium and 3.2 moles of chlorine. The limiting reactant, we need to look for the limiting reactant and the theoretical yield for this uh, reaction, okay? So we have 1.8 mole of titanium and 3.2 moles of chloride. So we need to look for the moles of titanium, and we need to calculate the moles of titanium chloride. Okay, we need to look for the moles of titanium chloride obtained from the moles of the titanium. So that's the first part, moles of titanium and moles of titanium chloride. So to determine this, we use the 1-to-1 ratio that is obtained from here, 1-to-1, okay, the conversion factor. And also we need to look for the moles of chlorine that will react to produce a specific amount of titanium chloride, okay, that it will be this. And the ratio is 2-to-1. So here we have the conversion factor 2-to-1. And then we can substitute the values of each of them. So we have here the 1.8 mole of titanium. By doing this, we can calculate that we produce 1.8 moles of titanium will produce 1.8 moles of titanium chloride. While we have 3.2 moles of chlorine, and when this react, it will produce 1.6 mole of titanium chloride. So this from these two amount, this is the smaller one. This is the least amount of product. So that means that the chlorine is the limiting reactant. And this is important because not all the time the one that is in the less here is going to be always the limiting reactant. That is going to depend on how the reaction occurred. Okay, as we can see here, 1-on-1 is the ratio between the titanium and the titanium chloride, while the ratio between the titanium and the chlorine is 1-to-2. So you're consuming twice the amount of this while you're consuming just one of this. So that's why the chlorine, even though is the higher amount as in moles of the reactant, is still the limiting reactant. Okay, so don't get confused or tricked about this. Okay, so because sometimes, okay, which one is the limiting reactant? Oh, the ones that has smaller amount of moles, and sometimes it's true, but not always. Okay, so you need to calculate and obtain the possible products from each of them. In many industrial applications, the more costly reactant or the reactant that is most difficult to remove from the product mixture is chosen to be the limiting reactant. When working in the laboratory, we measure the amounts of reactants in grams. To find limiting reactants and theoretical yields from initial masses, we must add two steps to our calculations, and those are the ones that we saw before. Okay, so let's see another example. Sodium plus 1 mole of sodium plus 1 mole of chlorine will produce 2 moles of sodium chlorine. Now we have here grams. So we need to turn from grams of sodium, 2 moles of sodium, and then 2 moles of sodium chloride, and finally 2 mass of sodium chloride. And it's going to be the same with chlorine. We have the mass of chlorine, so we need to turn the gram of chlorine to the moles of chlorine, and then the moles of chlorine to the moles of sodium chloride, and the moles of sodium chloride to the mass of sodium chloride. In other words, we have here the one of the map, grams of sodium, moles of sodium chlorine. We need to change these units by using the molar mass of sodium. Then from moles to moles, we use the conversion factor obtained from the chemical reaction. Okay, so basically it's 2 moles. I missed one sodium here, so sorry about that. It's 2 moles of sodium plus chlorine. 1 mole of chlorine will produce 2 moles of sodium chlorine. And finally, we have here the molar mass of sodium chloride that returns the moles of sodium chloride to the grams of sodium chloride. The same thing with the chlorine. We have the mass of chlorine. We'll need to change to moles of chlorine by using the molar mass of chlorine. Then we need to turn from moles of chlorine to moles of sodium chlorine because this is the product. We need to determine how much of the product will be produced by each of the reactant that we have. That's why we're doing this twice, okay? And this by using the ratio from the balanced chemical equation. So it's 2-to-1. Remember that we have supposed to have here a 2. And finally, we turn that moles of sodium chlorine to the mass of sodium chloride by using the molar mass of sodium chloride. And the smallest amount will determine which one of this is the limiting reactant. Okay, so once we determine how much we produce of sodium chloride here and sodium chloride here, The smallest amount will determine which one of this is the limiting reactant. So let's do this. The first one is 53.2 grams of sodium. We need to turn this to moles of sodium by using the molar mass of sodium, 22.9. Okay. And now that we have moles of sodium, we remove the moles, mass of sodium. We have the units in mole of sodium. We need to go from moles of sodium to moles of sodium chloride. And the reaction is 2 to 1. Okay. So that's why we use this 2 to 2, sorry. That's why we use this conversion factor to 2, okay? And now that we cancel the moles of sodium, we have the moles of sodium chloride. We need to change this to mass of sodium chloride by using the molar mass of sodium chloride, that is 58.4 grams. Okay, and this will be equal to 135 grams of sodium chloride. Let's do the same thing with the chlorine. We have 65.8 grams of chlorine, and we need to change that to moles using the molar mass of chlorine. And then we turn this mole of chlorine to moles of sodium chloride by using that ratio between 2 to 1, or 2 to 1 between sodium chloride and chlorine. And then we use the molar mass of sodium chloride to obtain the mass of sodium chloride obtained from this 65.8 grams of chlorine. And this will produce 108 grams of sodium chloride. So as we can see here, this is the smallest amount of the two possible amounts of product that will be produced by each of this. So that means that because this is a smaller one, the chlorine is the limiting reactant. Okay, the chlorine is the limiting reactant. So let's determine if the actual yield, for example, is 86.4 grams of sodium chloride. Let's determine the percent yield. So the actual yield is usually less than the theoretical yield because at least a small amount of product is lost or does not form during reaction, between other possible reasons that we have a smaller actual yield. Okay, so the percent yield is actual yield divided by theoretical yield times 100, and the actual yield is 86.4 as was given in the problem, and we use the theoretical yield, that is the smaller amount that will produce from all the reactants involved in the reaction. It was 108. This was obtained by the chlorine. Okay, so this will be 86.4 divided by 108 times 100 will be equals to 80%. So that means that the percent yield for this reaction is 80%. Let's do another example. This one, we have copper 1 oxide plus carbon graphite, this is solid, will produce 2 moles of copper and 1 mole of carbon monoxide. If we have, for example, 11.5 grams of carbon and 114.5 grams of copper 1 oxide, okay, we have this. We need to determine which of this is the limiting reactant, and by determining that, then we can obtain the theoretical yield for this reaction. So the solution map, we need to turn from the grams of carbon to moles of carbon, moles of carbon to moles of copper, moles of copper to moles to grams of copper. Now, let me make this observation here. This doesn't mean that you are turning carbon to copper. There is nothing like that. Okay, this is just if you begin with an amount of carbon in a chemical reaction that involve the copper 1 oxide, okay, that will produce a specific amount of copper. We can do the same by, instead of saying copper, uh, we can say carbon monoxide because it's another product, so it doesn't matter. Okay, at least one of the product must be uh, measured, and it's more easy to measure a solid than a gas. So that's why we are looking here for or mass of copper. Okay, so we're going to turn the mass of carbon to the moles of carbon, moles of carbon to moles of copper, and moles of copper to the mass of copper. As you can see, it's always the same template, always the same map. Mass, mole, mole, mass. And to turn from mass to moles, the molar mass, from turn to moles, the conversion factor obtained from the ratio of the chemical balance chemical equation, and from moles to mass, again, the molar mass of compound B. Okay, in this case, it's copper. And the same thing with copper 1 oxide. Okay, here we have the copper 1 oxide. We multiply or by the conversion factor of the molar mass of copper 1 oxide. And we have here the moles of copper 1 oxide. We can turn this to the moles of copper by using the conversion factor obtained from here. And then we obtain the mass of the copper by using the molar mass of copper. Also, this is another important point. This is really important. As I mentioned before, you can use any of these two products here, but you need to use the same in both of them. If you use here monoxide carbon, you need to use here the monoxide carbon because you need to compare, okay, how much of the same compound will be produced by each of the reactant. So we can use copper and copper or carbon monoxide and carbon monoxide. But you can't compare or do mass of carbon, moles of carbon to moles of copper and mass of copper, and mass of copper 1 oxide, moles of copper 1 oxide to moles of carbon and mass of carbon because then you can't compare the mass of carbon to the mass of copper. Okay, you're following me? So you can use copper here, or you can use carbon monoxide here and carbon monoxide. It doesn't matter. Okay, but at the end we're gonna say that how most of the time we are mentioning, you need to determine this one because this was the product. Okay, so in this case, maybe it's gonna mention that we produce a specific amount of copper, and that we need to determine that percent yield. Okay, so by saying that, the important thing is that you need to use the same one always, okay, when you need to compare both to obtain the limiting reactant. Once we have it here in the mass of copper, okay, the mass of copper, the smallest amount will determine the limiting reactant. That could be carbon or copper 1 oxide. So the main conversion factors are the stoichiometry relationship between moles of each reactant and moles of copper. Okay, and as we mentioned that, we obtain that from the chemical reaction balance. The other conversion factors are the molar masses of copper 1 oxide, the carbon, and the copper. So here basically are all that information. The ratio between this and the copper 1 oxide and carbon and copper. These are obtained from the chemical equation, the balanced chemical equation. And these conversion factors that are basically the molar mass of each of the compounds that are part of this reaction. So going back to the reaction or the problem, we can substitute here the values, okay, of each of the molar masses, and we can obtain that from 11.5 grams of carbon, we're going to obtain 122 grams of copper. And from 114 grams of copper 1 oxide, we're going to produce 101.7 grams of copper. So that means that this one, even though it's 10 times, okay, the amount of this, but this one is the limiting reactant. Okay, this one is basically the limiting reactant because it's the one that produces smallest amount of copper. Okay, so this less amount of product, and that by saying that this is the limiting reactant. So if we measure experimentally the amount of copper produced, that is 87.4, this is the actual yield. This is the one that you obtain by doing the reaction. So we need to calculate the actual yield, actually the percent yield, okay? So the theoretical yield is 101.7 grams of copper by looking back at our previous slide where it shows the limiting reactant that produced this amount of copper. And we use our equation where we put the actual yield divided by the theoretical yield times 100. And that means that this reaction has percent yield of 85.9% of, yield for this chemical reaction. So now we're going to introduce another concept that is known as enthalpy. Enthalpy is the measure of heat evolved or absorbed in a reaction. Chemical reactions can be exothermic. That means that they emit thermal energy when they occur. Okay, so sometimes we can mix two different reactant A and B, and suddenly we can feel that there is a release. We can feel that it's warm. Okay, the beaker or the whatever the reaction is taking place, We can touch those walls and we can feel that is an exothermic, it's releasing thermal energy. So that's reaction is called the exothermic reaction. Also, sometimes reaction can be endothermic. This is when they absorb thermal energy when they occur. Okay, the amount of thermal energy emitted or absorbed by a chemical reaction under condition of constant pressure, which are common for most everyday reaction, can be quantified with a function called the enthalpy. So the enthalpy is basically that transfer of energy that is obtained, that is released or absorbed during a chemical reaction. We define the enthalpy of reaction, the delta H reaction, as the amount of thermal energy that flows when a reaction occurs at a constant pressure. Okay, so remember that when you're doing a reaction, you can absorb energy from the surroundings, or you can release energy to the surrounding. Okay, so that's why it's a transfer of thermal energy between the system and the surrounding. And the sign of delta H of the enthalpy help us to determine if the reaction is releasing or is absorbing heat. The sign of delta H, positive or negative, depends on the direction in which thermal energy flows when the reaction occurs. Energy flowing out of the chemical system is like a withdrawal and carries a negative sign. That means that it's an exothermic because it's releasing, exit, exo negative. Okay, so it's releasing. That's basically when the energy is going from the system to the surrounding. Energy flow into the system is like a deposit and carries a positive sign. So the exothermic reaction is negative. The endothermic reaction, the delta H, is positive. So we have exothermic and endothermic reaction. In exothermic reactions, the energy is released into the surrounding. So when those two reactants combine, it will produce energy that will be absorbed by the surrounding, as for example, the flask where that reaction is occurring. And the endothermic reaction is energy that is absorbed from the surroundings. Okay, so here we have a graphic, a representation that help us to try to make a little bit more clear what we're talking here. This is energy is increasing at this point, and we know that you start with reactants and you will produce products. So we can see here like the energy of the reactant is here, and when the reaction occurs, the energy of the product will be here. It's lower. Okay, when you compare the energy of the product is lower than the energy of the reactant. So that's because it's released energy. This is an example of an exothermic reaction. When the reactant absorb energy, that will mean that the products will have higher energy than the reactant. So it will be something like this. Is because it's endothermic reaction. Okay, so that's why the delta H is positive. When thermal energy flows out of the reaction and into the surrounding as an exothermic reaction, the delta H of the reaction is negative. The enthalpy of reaction for the combustion of methane, the main component in natural gas, is as follows. So this is the reaction for methane, specifically the combustion. 1 mole of methane plus 2 mole of oxygen will produce 1 mole of carbon dioxide plus 2 moles of water. This reaction, when occurs, it will release 802.3 kilojoules of energy. This reaction is exothermic and therefore has a negative enthalpy of reaction. So if we look for the sign, that would tell us what type of reaction is from an energy perspective. Okay, this doesn't mean that it has less. Basically, it means just from where to where the energy was transferred. Okay, from the reactants to the from the reaction to the surrounding, or from the surrounding to the reaction. Okay, in this case, it went from the reaction to the surrounding. That's why it's an exothermic. It released that energy. It's negative. The magnitude of delta H reaction tell us that 802.3 kilojoules of heat are emitted when 1 mole of methane reacts with 2 moles of oxygen. When thermal energy flows into the reaction and out of the surroundings, as an endothermic reaction, the delta H reaction is positive. The enthalpy of reaction for the reaction between nitrogen and oxygen gas to form nitrogen monoxide is as follows. Here we have another example. In this one, you have 1 mole of nitrogen producing 1 mole of oxygen. I mean, 1 mole of nitrogen reacted with 1 mole of oxygen will produce 2 mole of nitrogen monoxide. And this type of reaction needs 182.6 kilojoule of energy. So this reaction is endothermic and therefore has a positive enthalpy of reaction. That means that the magnitude of delta H reaction tells us that 182.6 kilojoules of heat are absorbed from the surrounding when 1 mole of nitrogen reacts with 1 mole of oxygen. So, the amount of heat emitted or absorbed when a chemical reaction occurs depends on the amounts of reactants that actually react. We usually specify delta H reaction in combination with the balanced chemical equation for the reaction. So most of the time when you find a specific delta H of reaction is associated with a specific balanced chemical equation. The magnitude the magnitude of the enthalpy is for the stoichiometry amounts of reactants and products for the reaction as written. So for example, the balance equation and enthalpy for the combustion of propane, that is the fuel that is used in LP gas, is as follows. We have propane, 1 mole of propane plus 5 moles of oxygen will produce 3 moles of carbon dioxide plus 4 moles of water. This is the combustion of propane. And this combustion will release 2044 kilojoules of energy. So that means that this type of reaction is an exothermic or endothermic. It's exothermic because of the sign. Okay, so the sign is the one that's going to help us to determine what type of reaction is. When 1 mole of propane reacts with 5 moles of oxygen to form 3 moles of carbon dioxide and 4 moles of water, will produce or emit 2044 kilojoules of heat. These ratios can be used to construct conversion factors between amount of reactants or products and the quantity of heat exchanged. So this also now it can be used as part of the reaction. So we have seen that, for example, we can make a ratio between 1 mole of propane will produce 3 mole of carbon dioxide, or 1 mole of propane will produce 4 moles of water, or 1 mole of propane will react with 5 moles of oxygen, or 5 moles of oxygen will produce 3 moles of carbon dioxide, and also that 5 moles of of oxygen will produce 4 moles of water. We have seen that before, but now we can add also the enthalpy of the reaction by saying that 1 mole of propane will produce 2044 kilojoules, or 5 moles of oxygen will produce 2044 kilojoules. And remember that this is because these two are part of this combustion reaction. Or also we can say that 3 moles of carbon dioxide will, when 3 moles of carbon dioxide is produced, 2044 kilojoules of energy is released. As well, we can look for another conversion factor that goes from that when you produce 4 moles of water, it will release 2044 kilojoules. Okay, so this also can be used as part of the ratio that can be obtained from a balanced chemical reaction. So to find out how much heat is emitted um, upon the combustion of a certain mass in grams of propane, we can use the following solution. So now we're going from the mass, okay, of propane to amount of heat, to the enthalpy. So we need first to change the mass to moles, because remember always that the only way that we are to have to go to compare, okay, the different type of compounds and heat is through the moles, because that's we obtain that from the chemical reaction, and the chemical reaction is expressed in mole. So we need to change this mass of propane to the moles of propane. And we use, and to change from mass to moles, we use the molar mass. And from mole to kilojoules, we need to look for the chemical equation, and we know that 1 mole of propane will produce 2044 kilojoules. This negative, remember that we need to keep this negative because it means that it's releasing that amount, okay, of energy. So let's see the following example. Stoichiometry involving the delta H. An LP gas tank in a home barbecue contains 11.8 times 10 to the third power of gram of propane. Calculate the heat in kilojoules associated with the complete combustion of all the propane in the tank. So here we have the chemical equation, and here we have the enthalpy of that reaction. As we mentioned before, we need to follow this map. We have the mass of propane turns or change to moles of propane, and then turns or change to the appropriate amount of energy. So we need two here relationship. One is the molar mass of propane, and the other one is the ratio between uh, the moles of propane and the amount of heat that is produced. And in this case, remember that I'm using the word released because we know that is a negative, it's an exothermic. If it were an endothermic reaction, we need to mention that it's absorbed. Okay, but in this case, it's negative. So 1 mole of propane released this amount. If this were positive, we may say that 1 mole of propane absorbed. Okay, but because of negative, we need to mention, oh, the way that the correct way to mention this or say this is 1 mole of propane will produce 2044 kilojoules of energy. So let's do the mathematical process here. We have the mass of propane, molar mass of propane, so we can have the moles of propane, and then we change from moles of propane to the kilojoules, the units of energy, because that was the question: how much energy will be released or obtained from that amount of propane? So when we do all the mathematical functions here, we multiply this times this and then divided by this. This is equal to negative 5.47 times 10 to the fifth power of kilojoules. So that means that this is the amount of energy that is released. Negative means release, okay? That is released in the process. So, everyday chemistry Bunsen burners. Most Bunsen burners have a mechanism to adjust the amount of air and therefore of oxygen that is mixed with the methane. If you light the burner with the air completely closed off, you get a yellow, smoky flame that is not very hot. As you increase the amount of air going into the burner, the flame becomes bluer, less smoky, and hotter. When you reach the optimum adjustment, the flame has a sharp inner blue triangle and gives off no smoke and is hot enough to melt glass easily. And continuing to increase the air beyond this point causes the flame to become cooler again and may actually extinguish it. So here we have a picture basically of this four type of states, okay, of the flame. This one is with basically lower amount of oxygen. When you increase the amount of oxygen, you can see now that it's turned blue, okay, and this basically is the optimum scenario, okay, when we have the perfect amount of oxygen. And here is too much oxygen, so that's where the flame is going smaller in this scenario. So, chapter 8 in review, stoichiometry is a balanced chemical equation gives quantities relationship between the amounts of reactants and products, the quantitative relationship between reactants and products in a chemical reaction is called reaction stoichiometry. Limited reactant, theoretical yield, and percent yield. The limited reactant in a chemical equation is the reactant that limits the amount of product that can be made. And this one is obtained by doing calculation. And remember that if we have two reactants, we goes from reactant A to product, reactant B to product, and the product needs to be the same so we can compare them, okay? And the one with the less amount of product, that will be the limited reactant. The theoretical yield in a chemical reaction is the amount of product that can be made based on the amount of the limiting reactant. So to obtain the theoretical yield is the product that is obtained from the limiting reactant. And the actual yield in a chemical reaction is the amount of product actually produced. The actual yield is the one that you obtain in an experiment per se, okay, by doing it. And the percent yield is in a chemical reaction is the actual yield divided by the theoretical yield times 100. And remember that always going to be less than 100. The enthalpy of a reaction is the amount of heat released or absorbed by a chemical reaction under condition of constant pressure is the enthalpy of the reaction. And this enthalpy and this value could be positive or negative. If it's positive, that means that the reaction absorbed energy. And if it's negative, that means that the reaction release energy. That one with the negative enthalpy is known as the exothermic reaction, and the positive is known as the endothermic reaction. So the magnitude of delta H reaction is associated with the stoichiometry amount of reactants and the products for the reaction as written. So we can use that amount of energy with one specific amount of any of the reactants or product to create a conversion factor, okay, and determine how much will be produced or absorbed of energy by a specific amount of any of the reactants or the product. So this will be all for Chapter 8, Quantities in Chemical Reaction, from the book Introductory Chemistry by Dr. Troll.